I want to talk about our LiDAR and our solid-state LiDAR, but we're going to run a demo in parallel. So at some point, if people want to go to the demo while I'm talking, that's easy. Or if you have any questions during the time I talk, I don't have to finish. Just raise your hand, let me know, and we'll go directly to your question. So effectively, Opsys was formed to address the LiDAR business. But when we set the company up, we don't want to make just another LiDAR. So 99.9% of the LiDARs you see in the show or you hear about are similar in so many ways. Effectively, LiDAR is a replication of radar in optical domain. So effectively, what you have to do, you have to send a pulse of light and get the pulse back. And the time of flight of the pulse, you can figure out where the target is. So most of the companies which you talk about says, first of all, I can't use what's called a flash LiDAR. Flash LiDAR resembles a flash camera when you illuminate the whole field of view in one shot and you get your image back, and then you're processing all the pixels to see where things are at. It's limited in distance, it's limited in performance, and it's limited in the amount of light that you can transmit. So those LiDARs were done a long time ago, but obviously everybody knows they will not fulfill the requirements that you need for automotive. So the second thing is people say, I need to concentrate more light on a single pixel to go further away. So they take the maximum light you can transmit, collapse it into a very narrow beam, and when they illuminate that beam of light or that pulse, they illuminate a small portion of the field of view. Single pixel, multiple pixel, but it's a small portion. By doing that, they raise the amount of light they can transmit per pixel by a factor of 100 or 1,000, very big factor, so they can go a longer distance. The problem with that, it becomes like a laser rangefinder, because once you found one point and you have to scan the whole field of view, what's your next step? So the next step is to make it scanning. To make it scanning, they either put some mechanical means of moving the beam of light across the field of view. So it can be MEMS, which is electrically controlled micromirrors. It can be any combination of rotating prisms or with either MEMS or some other type of lasers. Or it can be even rotating galvanometers, basically. So any type of this combination is a different way of doing the steering of the beam to scan the field of view, but they're doing the exact same principle, which is I have source of light, and now when I measure one point and I want to go across the field of view, I have to scan through it. So the limitations are significant. One thing is how fast can you do it? Second thing is you have moving parts, so it has aging, it has limitations of reliability, and it has complexity in production. So it will allow you to have a LiDAR type performance, but it will limit your ability to advance with this, reduce prices, and actually get the ultimate performance that automotives need. So when we came to it, we said, first of all, we have to be a very fast scanning. What does it mean? We want to give the automotive cars something around 30 hertz update rate of the field of view as a minimum. And mechanical LiDARs, they don't get there. A lot of people quoting you devices that you hear in the show, I can do 10 hertz, 12 hertz, 20 hertz. But when you say, okay, when I go to maximum distance, in maximum resolution, what's going to be your update rate? So they tell you sub 1 hertz. Sub 1 hertz is not usable in automotive. You have to be above 10 hertz to be barely acceptable. And what we say is we give fast scanning under all conditions, under all terms. Second thing is, out there, high resolution and reliability, it has to be small enough size and low power. It has to be working over the full automotive temperature range, which is minus 40 to plus 85. But it also has to be semiconductor based, so absolutely no moving parts. And it has to be made out of technologies which are scalable in production. So we chose the wavelength to enable that to be 905 nanometer, or around 900 nanometer. What's the reason for that? Is we wanted to use the laser family that's called VCSEL, which is a very efficient way of making laser at low cost and large scale. And also, the 900 nanometers allows us to use silicon detector, which is basically a CMOS process, which is readily available everywhere. By using those two material systems, we basically built, if we can accomplish a scanning LiDAR, no moving part with those material systems, it gives you the best of all worlds. So just for a status, we delivered automotive BZR sample already in Q2 of this year to a number of customers around the world, Asia, US, Europe, and we're advanced steps with many of them. One press release you see this morning is that actually Hasco, which is really SAIC company, has chose us to go, out of all the LiDAR companies, they chose to go with us, and that's gonna go on SAIC platform, so they're actually saying we're gonna go to production in 2024. Actually, it's limited by us. How fast can we go to production? They would go to production even faster. And in 23 in Q2, it's not going to be a samples anymore. I mean, you're going to have the absolute final LiDAR, which incorporate all the automotive specification, which is ASPICE, cybersecurity, functional safety, everything you need in automotive will be incorporated in our LiDAR. So the first thing you say, okay, if the LiDAR works by sending a beam, and all the other guys, when they scan the beam, they need a mechanical scanner to do it. How the hell are they going to do it? So the way it works is this. You can see that there's two squares on the side called addressable laser array, and one square in the middle called single chip SPAD. SPAD stands for single photon avalanche detector. Effectively, it's a very, very sensitive detector that can detect signal even at a single photon type level, and it actually can be formed on a silicon wafer. On the sides, you see the array of lasers called VCSEL. So VCSEL by itself is called vertical cavity surface emitting laser, but forget all the alphabet soup. Effectively, what it allows you to do is allows you to grow the laser vertically in the wafer. So when you grow the laser vertically in the wafer, you can grow a lot of lasers next to each other. So you say, why not all the lasers are like that? All the other lasers, you grow them horizontally in the wafer, and then you have to cleave the wafer and process them. That's a process that costs a lot of money, take a lot of wafer real estate, and has a very low yield. You're talking about 9, 10, 15% yield is like magical.
And the yield for VCSEL is just the inverse?
I'm getting there. So the yield for VCSEL, when you get to a VCSEL process, because there's no post-processing, you grow the laser and it works. The yield is 95% plus. That's number one. So you can't address everything in the world with VCSELs because VCSELs are not good for communication for long distances. But what VCSELs are perfect is for what we're trying to do, is basically get a pulse of light and get it where we want it. So what we have to develop is we have to develop an array of VCSELs. We have thousands of VCSELs in there. But the way the array is structured is that if you define X and Y, like a checkerboard, we can control each laser separately. So it's fully addressable matrix of lasers array. So what does it mean? If I put this chip and I assemble it, by a command from our internal processor, we can actually turn any one of the VCSELs to turn on when we want it, and then go to the next VCSEL, turn it off and go to the next one. So how do you use that to create scanning? So the way you align the system, you can envision the light goes from the chip towards that way into the board. So you align the optics around the lasers so that if you envision a whole field of view is, let's say, where the car is, let's say the screen here. So you arrange them in a way with the optics so that any path of light that comes from the laser when it turns on and go to the target is addressing a fixed area in the field of view. So effectively, if I divide the field of view to the number of VCSELs I have here, I have addressed the whole field of view. So if I instantaneously only address one small area of the field of view by one VCSEL, and then I go to the next one and it's going to be the adjacent point, by turning on and off all the lasers in all the arrays once, I did one scan of the whole field of view.
Without a moving part?
With that, nothing is moving. So, any confusing? Any questions? So that's solve the problem of the transmit. So basically, if I was able to turn all the lasers on at the same time, you would see dots next to each other covering the whole field of view. And each dot is relating to one laser all the time. Now, when I send this laser to that point, if there's any object in that path, it will reflect back a signal. But because those paths are set by the definition of the LiDAR, if there is something in that path, it will always be reflected to a specific point on the receiver. So what does it mean? Now I can align a laser with a receiver. So I have a system that by allocating specific laser to a specific receiver, I can actually address, at a given time, I can actually address the whole field of view, but one point at a time, one pixel at a time, or one small group of pixels at a time. Okay? So now if I can do it fast enough, I can actually get into the LiDAR scanning, which looks like scanning without any moving parts. So you can ask the question, how fast can you do it? We're doing it at 1,000 frames per second. So our raw data comes into our LiDAR is 1,000 frames per second. And what we can do is, if you take that data and you give it to the automotive, they're going to choke on the data. They said, there's too much data. I don't need that much. So what we say is, okay, we take every point and average it 30 or 40 times before we give it to the automotive, to the ADAS system. And by averaging every point 30 times or 40 times or 60 times, you improve the integrity of the signal. So in LiDAR, one of the most important things, range is one thing, scanning rate is the another thing, but probability of detection is very important. So if you can tell me, oh, I have a LiDAR, I can go 300 meters, but my probability of detection is 40%, that's useless. That's not a LiDAR. I can't use it. Because I will detect things that it's going to be a lot of false alarms, or there's going to be a lot of things I miss. So by averaging every data 30 times, you raise the probability of detection over 90% for the full range of a LiDAR. Yeah.
No, it's not a question, it's against the light.
You want me to?
So I have a question.
Sure.
I want to drill this point home. So 1,000 frames per second, and I like this reference. So what would the average human, what would I be able to process as a reference point?
Depending on your age. But I think,
How about peak? What's the peak process?
I don't know, human eye is any 20 to 30 hertz. So if that's fast, actually. I think it's slightly less than that. So at 1,000 frames per second, there's nothing gets close to that in a human.
So
It's at least 30 or 40 times faster.
than what we can do.
Yeah.
That's
Yeah.
my point. Did that come through? So this is operating 40 times faster than what we do as drivers. And they're just a lot more accurate.
But that's one thing. And the second thing that's important is the probability of detection. You need to have a probability of detection, otherwise you get useless data. And our probability of detection is better than 90% at our full range that we specify our LiDAR. Just because we oversample that much. So this is on the evolution of our company. You can see we're making a basic LiDAR unit here. You're going to see in a movie later on. This is a full LiDAR that you see here. The size of it is half of a credit card. If you take a credit card, you can fit 2 of those on a credit card. But effectively, this is what we call the basic LiDAR unit. Then, if you want to cover a specific range in your automotive, you define what resolution you want to see. The only thing we change for resolution is the lenses. Everything else stay the same. The active optics, the lasers, the detectors, the processing, everything is the same. A broader lens, like a camera, a broader lens will give you a broader coverage, but you're going to have lower resolution because the number of pixels is fixed. And so you can trade off resolution for a coverage area, how many degrees you cover with one block, and then you can add those blocks next to each other to form a whole area of field of view that you want to look at. And we give you software to actually stitch all those together so it looks like a perfectly contiguous view. You don't even see the point where you're stitching them. So this describes what we said before. We're going to go into production. Some customer would like to have this already pre-packaged, so we take a few of those and depend on the specs, we put it in the box. But the idea behind it is a distributed sensor. You can go to the car, you can put it inside the headlights, inside the taillights, in the B pillar, behind the windshield, anywhere you want. You don't have to change the car shape in order to include LiDAR functionality in it. So this, like I said, this is our LiDAR. All the structure of the LiDAR is a gallium arsenide-based VCSELs and a silicon-based detector and some certain electronics to support all that, the microprocessors and memories or whatever we need in there. But effectively, gallium arsenide capacity around the world is sort of infinite, because when Apple decided to put face sensor in their phone, everybody and their brother built a fab. Now the fabs are running at a 40 or 30% capacity. Capacity is not an issue. And by the way, that's what enabled us to use those lasers in here, because before that happened, the cost of gallium arsenide processing was about 100x more expensive. So once the costs have gone down to this efficiency, that enables you to process this much more cost efficient. And wafer size is growing. You're talking about 6-inch wafer and 8-inch wafer. The second thing here is on the wafer side is the detector, which we talked about, the array of detector. It's done on silicon, a regular CMOS process. Again, capacity is a non-issue. So the two main materials or components that makes our LiDAR, they exist in high quantities, and we buy them in a wafer. You know, how many wafers you buy, the more components you have. And what it gives you, it lets you enjoy the cost efficiency versus quantity of any chip used in manufacturing. Like you make computers or you make phones or any other product that use semiconductor chips have the same cost efficiency. The more you buy, the more the cost effective it becomes. The second thing what we do, because we don't have any moving devices, and by the way, this is, I don't know if you can see it well, but this is how our device looks. So you have the lasers in the center and they have some ASICs around to drive it. So it's all basically planar, so fully automated machines can make a LiDAR. The touch labor content of the total cost of goods sold here is less than 10%. So what does it mean? It means I can have a scalable cost. The more efficient my material, I'm controlled by material cost. So the more efficient our material cost becomes, the lower our cost. And that's what automotive people want. I'm going to buy for 1 million cars or 2 million cars. The more I buy, I want to still see the efficiency of going down in cost. And that's what this approach enables. Plus, it has no realignment. You put it in a car, there's no mechanical movement. You don't have to come next year and start see if the bearings are still working or any other movement or recalibration of a temperature. It's set and forget for the rest of the life of your car. And all this is going to be done at our contract manufacturer in Thailand, and it's a fully automated assembly process. So again, no touch labor. So this is just example. Like I said, if you take everything from this point backwards, the lasers, the detectors, all the electronics is the same. And if you want to address different resolution or different field of view, you just change the lenses. So by changing the lenses, you don't have to requalify the product. The product is qualified for automotive and can be optimized to any customer by changing just the lenses, the optics in front of it. And this is 3 examples. If you have 0.1 by 0.1 resolution, 0.2 by 0.2, or 0.4 by 0.4, just changing the lenses, and it allows you to address that. And you see that the field of view is changing with the resolution. So you have in 80 degrees field of view, 0.4 by 0.4, which directly translate to 45 in 0.2 and 22 and a half in 0.1. But anyway, it's a mathematical relationship between them.
Eitan, I'm sitting here because they've been through a lot of specs. Okay. So if you could help them understand on each of the categories where you sit against your competition, does that make sense? I can, but you have to be specific because number of points. Yeah. We have the highest number of points you get per square, but effectively, the number of points is mathematical. So it's the number of points per second. So first of all, you have number of points, which is resolution. So if you have a degree by degree, and you say I'm doing 0.1 degree, so it's 10 vertical, 10 horizontal. So on a degree square, you have 10 points. All right. It's 10, 10 by 10, 100 points. Sorry. But then you have to multiply it because this unit is by second, degree squared per second. And per second is the number of scans you do, multiply
by this number of points. So if we do more scans than anybody else, we have more points.
Gotcha.
And more points give the customer or the ADAS more accuracy, more data to work with, more update rate, more real-time type performance.
So that spec is the most important.
That spec coupled with probability of detection and distance altogether is important. That's our point. Our point is when you go to the show, you hear all those anecdotal numbers. You say, oh, I get to 300 meters. Oh, I do this resolution. But can you do them all together all the time? And the answer is no. We do them. That's what we say. We do all specs all the time. But if you ask the question, they said, oh, it depends. It doesn't depend. I want the full probability of detection for the long distance, for the full distance, and I want the number of scans to stay the same for any distance I'm concentrating on.
So in other words, as they ask other LiDAR companies or sensor companies, and they claim a range, ask them, what can it see at that range?
Well, if they give you a range, it says, what's the probability of detection at that range?
Yeah.
And then you have to be defined at what reflectivity, at 10% reflectivity. And then the second thing is, how does your scan rate for a specific resolution change versus range? And by those two numbers, you get deep in it. They won't answer you anymore. They'll go to the next guy. So this is a short movie, just shows our process, what we talked about. It shows you the detector, the LiDAR sensor. Did you stop it or it stopped by itself? Here we go. So if you can stop it here for a second. There you go. So you see the lenses. They come in together, and behind the lenses, you see those are optical filters, but you see the board where you see the lasers are sitting right here, and all the driving electronics is sitting behind them, and the rest of the circuitry to manage all this process of the LiDAR. Can you? But the important thing to see here, it's all typical surface mount process. So there is no mechanical alignment of 3D components or active moving components alignment. That allows you to have an automated. So if you can stop here for a second. So this, you see, this is the array where the lasers are. And that's when you see this light, the photons being beamed out at a specific direction aligned with the optics. And all around it is all the ASICs we designed to actually enable that to work. Let's go. So when you see the light coming out, then you can see in a second. So it hits a target, it reflects back. It hits another target, it reflects back. And now basically if you have enough pulses to cover the whole field of view come out, you're actually seeing the target. And here, can you stop here for a second? And here what you can see is what I said before. If somebody give you a specific area I want to illuminate, they said, okay, you'll need, let's say in this case, 4 units. Maybe those units are maybe 0.2, and this one is 0.1, or whatever mix they want. But we can mix and match the optics to give them the right coverage. Okay? And then we package it. They can put it on the roof. They can put it anywhere they want. It's whatever the customer wants. So you can see it now. It goes on the roof as an example. And you see on the sides 0.2 and the center was 0.1 by 0.1. That talks about resolution. Here's another one. You can come to our booth and see it operating, basically embedded into the rear light of the car. There's a LiDAR sitting in the rear light operating in our booth. And they define this resolution as a 0.4 by 0.4, so we don't care, but the LiDAR is sitting inside. And here's another one. Can you stop with this? So this is another interesting one. We put the LiDAR behind the windshield. So you go in the car, you put the LiDAR behind the windshield of the car, between the windshield and the rear view mirror. So whatever the Mobileye is sitting today, that's when you put the LiDARs. And effectively, we're operating through the windshield of the car with effectively no distortion to the signal, no effect on the signal. Just because it goes exactly to the operation of our LiDAR, but there's no impact of the windshield. What it gives you, it allows you to integrate it in the car very easily. You have the cleaning system, you have everything embedded in the car as it is today. And it's very straightforward for you to cover that.
Eitan, that's a pretty big breakthrough. Has anyone integrated LiDAR behind the windshield yet?
At least we don't know, but You know, the wiper blade is okay, but it's so slow, you oversample. When you sample at 30 hertz and the wiper blade moved at 1 hertz, according to Nyquist, you have to do 2 samples to actually don't have it interfere. We do 15x of the wiper blade, so we don't care about that. But has anybody does that? I don't know of anybody who did that. A lot of people trying, but they're more trying on the front headlights than behind the windshield. But you know, I don't know if people are talking right now or not, but we know our system is going to give you the most efficient way of doing it just because we have fixed beams. We don't have beams that actually rotates with a mechanical, so you can calibrate the imperfection of the glass.
If they go to your display, can they see that?
Operating.
Operating?
Yes.
Behind the windshield?
Yes. Yes. We teamed with a company, there's a press release called White-Eye. White-Eye is one of the largest manufacturer of windshields. And they're going to have it in their booth, and we have it in our booth. But effectively, you can see a car windshield in there, and that operating behind, and you can see on the screen above it, you can see yourself standing in front of the light. So we think this makes it very easy for integration, very effective, and we don't have any cooling or heating or vibration, or like if you have a mechanical LiDAR. Plus, it's very small, and it gives you the best performance.
What's the cost of your system compared to comparable LiDARs that are?
So cost is, first of all, the first answer is we're meeting all the customers' target as they were before or as they are right now. So they tell us, you have to say under L2, L3, L4, what the costs are, and we're at their target or below. Second thing, we know we went to RFQs, and we know what other people are bidding, and we are equal or less, the way we're bidding it with full margin on our product. And you have to consider that our product cost is much more scalable than their product cost, because the mechanical system, as much as you want to automate, the labor cost to align the system, forgetting performance and forgetting reliability, the labor cost in production to align their system and to calibrate the system is so high that when they try to scale their cost versus quantity, they're going to hit the glass ceiling. It says labor cost is labor cost. I just can't get over it. So basically it's going to be asymptotic change, but not serious. With us, because we don't have any moving parts, it's fully automated alignment, that you can see the cost continues to be efficiently scaled with quantities.
So Eitan, on John's question, before we'll go to Ben next, but can we be pretty specific? Because I think if you were at a volume above, what, 1 million, could you do a $200 LiDAR sensor or something in that?
We say we're going to be under $150 per system, per LiDAR, per box.
Is that
So.
what you wanted, John? Is that?
Under $150 is pretty good.
That's not for the whole car. So if you have 4, you're going to have it about 500 to 600. So that's, but you have to add those numbers, but it's still pretty damn good compared to everybody else. It's still significantly below other people. But anyway, all those things.
When do you want to reach this price point?
The price point is totally driven by quantities. We're starting to get in production, as we said, end of 24. So it's quantity driven. So if we assume quantity is going to get to the multi-100,000, let's say in the 25, 26 time frame, so that's where we asymptotically get there. Yeah.
You were mentioning fully automated alignment.
Yeah.
And ultimate, that makes it sound as if it's the hardware doing the alignment. Actually, it must be software, right?
It's a combination.
Could you tell us a little bit about the software that's behind this and how it's reconciling all of these views?
So this is a projection system. So you project your light into a specific area, and you get a reflection from that. And the computer knows what you should be getting as a reflection versus what you are getting. And he knows the parameter to adjust in order to align the two together, all in his software. So effectively, there is some mechanical adjustment to the lenses, just mounting them. But that's also done automatically by the system. Basically, turn the lights on, put the stuff in, and know where the light's supposed to end up, and then freeze the location. But then the overall calibration of the system, we call intrinsic calibration. Basically, you have certain shape that you're looking at. You know what you're supposed to get, and if what you're getting is not what you're supposed to get, you make the adjustment by software to actually get that. Is that?
Yes. Are you also producing software then that integrates multiple units, and if so, how many potentially?
So our software ties. So what this unit produces is what's called a point cloud. So the point cloud can be connected to another point cloud. It's fairly straightforward. So we give them the code to do it. They integrate those together with our code. It's unlimited. I mean, they can do whatever they want. You're more limited by the hardware than you're limited by the software. But you get to do, 4 or 8 per board, per hardware board. It's not a problem. And it's software, either we give them a board to actually do the consolidation of the data with our software, or they can put it on their ADAS system and run our software on their ADAS system. Either way.
And the data stream looks probably much like an optical data stream from another optical device once everything is calibrated, right?
I would say yes and no. The no part come from, you hear a lot of LiDAR companies says, oh, we're doing perception. We're not doing perception, we give you raw data. The reason they're doing perception is because their probability of detection does not meet the customer requirement, so they try to say, oh, I'll process the data for you and give you the customer an object recognition. Okay? We don't do that. We said, we give you the best data there is. You can do easily the object detection or the object recognition yourself. And that's why we stop at our core competency, which is make the best LiDAR there you can make and give you a raw point cloud. And then from that point on, you take it and do whatever you want with it. Because every time you process the data, you lose something. Because every processing, you lose some information. So if the customer gets it after it was processed, the benefit he's going to get from the data is not the same. Yes?
I see automakers introducing all levels of automation, autonomous from level 1 all the way through level 5, 2+. We know that there are ADAS systems that require cameras, blind radars, and so forth. At what point do you tell a automaker that they've reached the threshold after which they need LiDAR? In other words, what functionality and features require LiDAR in your view?
Look, I mean, every system, when you try to, we don't build ADAS system, and we don't build the system that runs the car. But what we know is when you drive a car autonomously, whether it's full autonomous or whatever level it is, you want to have a real-time 3D data of the environment you look at. A camera, by definition, is a 2D device. So in order to get a 3D, you either use multiple camera and infer somehow, or try to make some triangulation with baseline, but the baseline is never big enough. And then you get into ambiguities and try to guess, like a second order or third order, what's a 3D look like. A LiDAR gives you a true 3D immediately on a real-time basis. So if you want to reduce your risk and run a car at the lowest risk and very efficiently on autonomous mode, you want to have a LiDAR. The question is, how do you get a LiDAR that's going to be at least as efficient, as reliable as the car? So for the life of the car, you don't have to touch the LiDAR. Unless you get in an accident, then all bets are off. But accident is an accident for anything else. So you have a LiDAR that is at least as reliable as the car. You can incorporate it in the car body without altering its shape. So all your designers can do whatever they want to do, and you can embed the LiDAR within those limitations, and then give you the best-in-class performance for a very cost-efficient way. So that's what we try to present here. But if Elon Musk decided, I'm not going to use a LiDAR for a principle, and then he runs into accidents, I would tell you, I don't know all the details, and I'm extrapolating here, but I would tell you 99.9% of his accidents would be eliminated with a LiDAR. So then the question is, do you take a risk? Why take the risk? Plus, the LiDAR is going to give you the true 3D scanner. And that's what you need to drive a car. You don't want to have a database of 1,000 cars that went through and start mapping the whole world in a super data center and start doing some, artificial intelligence to interpret where you are and see if there's anything there. It's all third-order processes to do what the LiDAR will do on a live basis. I mean, they used to use that process in all the cruise missiles. Cruise missiles 30 years ago, they used to have pictures of where they're supposed to go, and they take the picture and compare it to what they see, to what they have in memory, and then they sort of try to figure where to go. Then they had GPS, which give them real-time 3D, and they said, I don't need this stuff. So I think it's a similar process we're going through here.
So what I'm hearing you say is that there's a lot of different ways to achieve this. They're putting together different systems with the idea of cost and benefits and so forth, but you're not saying that LiDAR is mission critical for a certain kind of function. There's no other way to do it.
I would say LiDAR is only mission critical if you want to do it efficiently and basically more foolproof than any other way. But if you take 2 engineers, they're going to find you 10 ways to do anything. The question is, can you do it right? Can you do it in a way that's actually give you the assurance you need for the system to work with margin? And can you do it cost effectively? And everybody's tempted to do with cameras because a camera chip costs a few bucks. But if it doesn't give you what you need, then it doesn't give you what you need. And so what we do in here is we call it a 3D camera. You can call it LiDAR, whatever you do. This is really a 3D camera. So it allows you to map real-time 3D your environment and being able to make decisions in a car that will not drive you into problems. Okay?
Tom, let's come back over here to Pete to get a question for you.
I was going to ask you, like, when you showed the multiple sensors in a row and you're trying to get the different horizontal field of view, how much can you steer the beams of the photons to perhaps eliminate the need to have more units?
So you don't steer the beam dynamically. It's all passive.
Right.
So if you put a lens in front of it, depends how much you open the lens. But if you think, let's say I have, just for example, 100 pixels. I can illuminate a 1x1 device in 100 pixels, or I can illuminate 100 by 100 with the same 100 pixels. So when you extend the beam to a wider field of view, you reduce your resolution, which is okay. I mean, you're going to see movies here that you hardly can see the difference in the resolution. And it's going to be a factor of 2 between them. But if you ask me the physics, how much can you expand? I think, if you look at a fisheye on a camera, if you go to close to 180 degrees, you're totally distorted already. So you have to stay less than that. So it's what's efficient. I mean, once you get beyond 150, 160, 170 degrees per single lens, then you start running into the limit of the optics. The optics get heavy and more expensive. But then coupled with that is going to be the trade-offs that you have, which is when you open one device very wide, you shorten the distance of your lookout, and you reduce your resolution. So it's just bag of water. You push from here, it goes there. You push from here, it goes. The physics is fixed. So if I go from a 0.1 by 0.1 resolution to a 0.2 by 0.2 resolution, it's double on the vertical, double on the horizontal, so it's 4x. So you reduce by square root of that the distance, so it's half the distance, and you cover 4x the area, but the resolution is half. Like, did I answer what you asked me, or?
I think so.
Okay. I'll show you the movie. It's much more straightforward to understand. So this is one, like somebody put it on the roof. You have one LiDAR here looks to this area 0.2 by 0.2, and LiDAR here, the same one here. And the center one, he wants to look at 300 meters or 200 meters at a 0.1 by 0.1 resolution. So this is one example to put them together. Here's another one where people said, no, I want L4, L5. I want to cover the whole car. So they said, hey, no problem. You put those inside the tail light in here. And you put those in the B-pillars in here. And you put those either in the headlight or on behind the windshield. You can bury them in a car whenever you want. And then there's no reason for you to look sideways and look 300 meters. Nothing is going to surprise you 300 meters on the sideways. But forward, you want to look farther away. So it effectively becomes an average of all the costs, how many dollars per degree coverage you do for the whole car. And this is the way to get the most efficient with fixed hardware. The only thing changed is the lens. Okay? Here's another example on trucks. So trucks on the forward, they look the same as cars. Same idea. Maybe they want more high resolution because their stopping distance is longer, they need to make a decision faster, whatever. But on the looking back, if it's a full trailer, you're looking 40, 60 feet on the side of the trailer. 40, 60 feet on the side of the trailer, you're susceptible to sun loading, you're susceptible to many things. So people used to put cameras in there, and the camera will tell you, yep, there's something there. I don't know exactly where that is. And the LiDAR can tell you, not only there's something there, it tells you exactly where it is in relationship to the truck, and it covers, the elevation, the full elevation of the truck. So when you want to turn the steering, you can put a system that actually will limit you, so you're not going to hit that obstacle in there. It's not just tell you there's something there, it tells you exactly where it is dynamically, and it tells you what to do. And apparently that's very important for truckers. So you can put one of those LiDARs, one to cover on the mirror looking back, and the rest of them looking forward. And this is what we talk behind the windshield. Again, it's first of all, you have to have a windshield that actually can pass infrared, our wavelength, and that's why I make that windshield. Then it's readily available too. And then the second thing is embedding the whole system behind the windshield, not start worrying about how I'm going to clean it, I'm going to watch it, all these other things that suddenly disappears. And you're replacing a camera system with a LiDAR system. And you don't even know. It doesn't even interfere with your car volume or anything else. So again, you come to our booth, you can see it working behind the windshield. This is what we talked about, the rear light embedded right here in the rear light. You don't even see it's there. And again, you can see it live operating in our booth. That's in partnership with a company from Korea called SL Photonics. SL World on SL Photonics. And they're manufacturing those systems for a lot of people. So here's a lot of things you can hear from people who make LiDARs. They all talk about ROI, which translates to a range of interest. So what they do is, because the LiDAR does not have the scan speed or the resolution, they said, oh, when I figure out there's something there, I'm going to go there and limit the scan of my LiDAR so I can go very fast on a much smaller area. But when you do that, you lose the rest of the field of view, and how much is the benefit. So what we say is, because if you remember, we are scanning here at 1,000 frames per second. So what we say, if you tell me, if the LiDAR detected something here and you want to see it more sharply or with a better signal processing, just define it here, and we're going to start scanning this area much more and reduce the number of scans in the rest of the area, but not eliminate it, just reduce it a little bit less. So we're still aware of what's happening around us, but in here we can get much more efficient and give you much better signal resolution, or not resolution, but much more signal sensitivity or accuracy. Then if you say, hey, I have 2 areas I want to do them, you can define 2 of those or 3 of those. It doesn't matter. So you can define dynamically where it is. And with our system, you can change it on a scan by scan. If you do one scan and you say, I want them to be here, and you then do another scan and say, I want them to move to the other place, you can do it. So there's no delay. There's no mechanical system that has to move and adjust. It's on a real-time basis. Obviously, you have to have the scans themselves, but it's on a real-time basis.
Can I ask,
Sure.
if you have a car that's like level 2, like say that Volvo EX9, are you going to want to have 1 LiDAR? Are you going to want to have 2? Want to have 4?
So it depends what Volvo wants to cover as far as field of view. You say, if we go and replace luminar on the Volvo, how many LiDARs we have to put in there to cover that?
I mean, it gets into the cost thing. If one's 150, 4 is 600.
You'd be surprised how much the Volvo system costs. I would tell you, I don't know what they cost, but I'm telling you, we're more than competitive.
Okay.
Immediately. Even forgetting performance and forgetting reliability and forgetting all this other stuff.
But you're going to want more than 1.
Yeah, you can put 4. But their system, when you say 1, I mean, those galvanometers cost money. The manufacturing costs money. We're going to be at least more efficient, if not much more, from cost point of view. And performance is a performance, that's a given. I'm not trying to undermine Luminar. I mean, they do what they do. I'm just saying, when we look at those applications, we compete head-to-head with those specifications. And the cost, obviously. Okay? Can we run that video? So this is a video just as an example. So what you see here, obviously it's a LiDAR, but this is a raw point cloud. There is no video processing, there's no video overlay, there's anything. You can see the forklift, you can see the person moving in there. I mean, it's all real-time basis. You can see what's going on. And the number of points, you can see right away how high the number of points is, because it almost looks like a video. And each point in there is a 3D coordinate. Each pixel in this picture is a 3D coordinate. So what does it mean? We can take our viewer, that wasn't included. we can take our viewer and we can move it so you can look from the top, from the bottom, from the side, anywhere you want, because each one of them has a 3D coordinates. I think that's it.
Yep, that was it.
Yeah, so just to summarize, we wanted to call it LiDAR 2.0, whatever you want to call it. Basically, what we came in here is to do a different LiDAR. A different LiDAR is a true solid state, absolutely no moving part, but still maintaining the the performance of a scanning LiDAR. What we delivered is, we think, is the best performing LiDAR in a very efficient cost, very scalable manufacturing, and addressing the cost target of the customers. And we're moving in with customers. We have some press releases relate to behind the windshield and in the headlight, taillight integration, but this one press release came this morning, says basically going into production with the first customer in China. And by the way, when you look at the world from a demand point of view, in the next 2 years, all demand is going to come from Asia, mostly China. The European and the US probably will follow in the 26 time frame and up. Whether it's what's that?
Could you just mention your customers?
So we said Hasco, it's in the press release, yes. Yes, and the way we work in China, we work with 2 leading tier 1 guys. One of them is Hasco, there's another one going to be press releases to come. And each one of them addresses, like SAIC is the owner of Hasco, but there's other customers, big customers they're addressing. Yes?
I don't know how to ask this, but I know they want to know.
Okay.
So there's a skepticism about autonomous
Mm-hmm.
LiDAR, and when are the big deals going to be, and what volume and when?
Mm-hmm.
And I know you can't say volume, but can you give us a sense, and maybe you can even make it broader for the industry. This deal is going to be a high volume deal,
Mm-hmm.
and pretty soon.
Mhm.
Can you characterize it in any way?
We expect in the 24 to make multiple thousands of LiDARs. Multiple thousands, it's under 10, more than 5. And we expect in the following year to go 10x. And the growth beyond that should continue on similar trajectory. There's so far you can go 10x, but still it's going to grow in a pretty steep slope. And that's only addressing China. So China has, I don't know, about 20 million cars a year.
Yeah.
And through our customers, we have access to, through one customer, it's like a quarter of this market. And they committed by 25 to have 6 million cars with LiDARs manufactured per year. So that's obviously not in those numbers. Those numbers are much more, conservative than the 6 million number.
Right.
But yeah, they're moving forward. And in China, it's not an economical thing. In China, they decided they're going to have LiDARs in the car, then they're going to have LiDARs in the car.
So, in the car that your LiDAR is going to be installed within, what is the most advanced autonomous functionality that's going to be?
So as you understand, we work with Hasco. Hasco is the ADAS system, guys.
Right.
They decide on the autonomy level. Our LiDAR can play in any of the autonomy levels.
Understood.
So we think it's either L2 or L3+.
L2 or L3+.
But because the L4 is a few years away, and then L5 is away.
And that perhaps answers this question when you showed that previous screen that showed the pixels, and they said, you can be able to focus on one target or 2 targets, so those decisions are made by the overall functionality of the product or the demand on the ADAS or et cetera, and then who makes those changes? Do you deliver it with that capability, or do they make the changes?
We give them the drivers to be able to address that. But effectively, like we said, we give them point cloud.
Yeah.
They go and they do object recognition on a point cloud. So if their system say, I see something there, I don't know if it's a ball or it's a cat or it's a, whatever, then they can put an ROI on it and they can focus on it and see more clearly what it is. But they decide on their system how they want to address specific objects. We just give them the point cloud and the access to the ROI.
Just like camera.
Yeah. Yeah. It's got a multifocus camera. When you push the button, you can see it. You can focus on 9 things at a time, but they put those squares on it. So they find something there and they focus on it.
I'm curious just about the overall growth in knowledge base of this industry, and how much you overseeing that become aware of best practices perhaps or not, or is there shared intel on how many you should focus on or that
Oh, how many?
and not just broadly saying, again, how much did that become part of the collective of knowledge, or is that very proprietary then by the
The honest answer to you, we can give them access to do whatever they want to do.
Right.
They need to decide how to do it because they need to define, if I have so many threats at a given frame, maybe I should stop, So, but that decision is not by us. We don't take the liability and we don't make those decisions for them. So that's why they get paid the big bucks to do this other stuff. But what we give them is the best point cloud and the ability to concentrate on whatever they want. But I'm sure artificial intelligence tell them it's too much, it's too little, I should do it, I shouldn't do it. But that goes to all the object recognition that they do. Yes?
High-performance LiDAR is typically used by high-performance cars. So the question is, why does the Germans have not made contracts with you?
We do not have Germans contract, but we have a lot of Germans interaction, and with number of big companies in Germany. Now, what's the rate of them going to production? I don't think they're in any time going to move as fast as the Chinese, but they're probably in the 25, 26 time frame. So we're there to serve them. We are working very tightly with them, with a number of either tier 1 companies or automobile companies directly. We have been tested by them and continuously being tested by them. But I don't think there's anything they're going to put up. Whatever they put in there in production already does not give you, it's hardly give you L2 for what you see from, from the system that they have access to right now. But we expect that to be a significant part in Germany, but not in the immediate future.
Several car manufacturers and suppliers yesterday said that the hype of autonomous driving is over. The hype of autonomous driving is over. So that means that now they want to sell more ADAS systems, and they see a full automated car in a far future.
The answer to you is we don't care. We'll sell them sensors for parking sensors, and we sell them sensors for up to L5. Whatever they do, they'll take. Whatever they want, they'll take. But we said our sensor technology fits all of that.
Yeah.
The issue they have is more of how do you manage the car when you have the image? How do you?
The reason is not that LiDAR is too expensive or the systems are too expensive. The reason is that they can't find a way to make the system so safe in terms of traffic accidents with pedestrians, with bicycles, and regulations. That's a very, very conservative now.
And the second thing is how do they convince you to get in a car without a steering wheel?
Yeah.
So because you're gonna get there, you're gonna get a heart attack. It's like I don't want to sit in that car.
In the government.
Yeah.
Regulation is another point. Yes.
But the L3 can be very helpful. There's more than 1.2 million people get killed from just pedestrians getting killed by cars in car accidents. So if you can reduce the number significantly and reduce the liability of insurance company and people and eliminate risk, that's the first level of ADAS system getting integrated in a car. Second level is how much do you want to stretch it? And on the L4 systems, when you get to more of a trucking and people in the US, I saw ads on TV, they pay $120K for a driver off the street to come and drive a trailer. So they say, if I have a system that reduces the threshold, make it much easier for a driver to be trained, I can hire low-cost guys to drive big trucks, and then they have to make less decisions. So that's not a full autonomy, but it's in between, and there's a return on investment because once you put it in a car, you reduce the cost of the driver.
Right.
So,
Eitan, I know you've got to run.
yeah.
I do think there's one question that half the group knows, but half the group hasn't met you before, and so you feel like you've said this before, and I'm gonna. So when I met you, I felt like you came at this problem from a very different history than most all other LiDAR companies. Can you help them understand your experience in the other companies and how you arrived at this?
So it's not me, it's we, all of us together. It's the whole team. And basically our history was in communication. So basically, startups, companies making lasers, making laser systems, communication system, internet, cable TV. We're the largest one in the world in all those modules, from growing the lasers all the way to supply the systems. But at some point, after 25 years, it's just start getting boring. It's the same thing. So we decided to do something more fun and get into the automotive business. It's actually, I come from another point, because automotive business is a tough business. But once you get in, you're in. In telecom, every buyer comes to you and says, every quarter, where's my 15% reduction in price? Because I have, competition here and there. In automotive, you have a platform for 10 years. Yes, there's going to be price reduction, but it's going to be more stable type performance. plus the interest, everybody loves cars, so we like to do something different.
And the other guys, no knock on them, but they were coming from, what, an optical background? or-
So yeah, I guess that point. So we come from the optics side of things, which is, if you look at the history of companies, there's a lot of startups find the best way to lose money in optics in a big way. And a lot of the other guys come in the electronics side, try to infer on the optics as something you can buy. We think the most complicated thing in the LiDAR, in the optical module, is the optics. Know how to make things in millions per month, which is not what we do on the telecom side, is what makes this thing go. So other than performance and specs and all that stuff, it says how can you make millions? And how can you make millions of parts per month, per year? How can you make them profitably in a cost-effective way and ramp and make money? And so we come from the background, which is the toughest part is the optics. And other people come from either from the software side or the electronic side. And we think there's some of those limitations we lie there. But I don't want to undermine anybody else. I mean, a lot of people do a lot of hard work. We just look at the problem differently, and we think we have the optimum solution.